This problem asks us to list all possible functions from g of 3 to itself. So g of 3 consists of the set 0, 1, 2. Now at first glance, it seems like there are an infinite number of functions from g of 3 to itself, because we can, for example, write f of x equal x, f of x equal x times x, f of x equals x times x times x, etc. We can also write things like f of x equals x to the x, f of x equals sine of pi over 2 times x, and many, many other possible expressions for describing functions. But now what happens if we try to plot these functions? If we try to plot f of x equals x, we get 0, 0, 1, 1, and 2, 2. So this is f of x equals x. Now let's try and plot x times x times x. Plugging in 0, we get 0. Plugging in 1, we get 1 times 1 times 1, which is 1. And plugging in 2, we get 2 times 2 times 2, which is 8, which is 2, mod 3. So from this graph, it is clear that these two functions are actually the same. So what did we learn? Well, we learned that a function is, in some sense, independent of the expression used to describe it. So there isn't really anything special about writing x times x times x. We could have written something like x times x times x plus 0, or x times x times x plus 1 minus 1. And these all describe the same function. A function is really defined by its behavior, or in particular its input-output pairs. So going back to the original definition of a function is just a mapping from a domain to a range. So in this case, the domain is GF3, and the range is also GF3. So the question is really asking, how many different mappings are there from GF3 to itself? Well, let's look at how many choices there are for f of 0. So f of 0 must lie in the set 0, 1, 2. Similarly, f of 1 must lie in 0, 1, 2, and f of 2 must also lie in the set 0, 1, or 2. So there are 3 choices for f of 0, 3 choices for f of 1, and 3 choices for f of 2. So all in all, we have 3 times 3 times 3, which is 27 possible functions from GF3 to itself. So now let's try and list them all. Well, a function, as I said before, is defined by its input-output pairs. So all we need to do is list all of the possible input-output pairs. So let's make a table. F of 0, f of 1, f of 2. We can have 0, 0, 0, 0, 0, 1, 0, 0, 2, 0, 1, 0, 0, 1, 1, 0, 1, 2, 0, 2, 0, etc. And finally we end at 2, 2, 2. A degree 0 polynomial is of the form f of x equals c0. Now in GF3 we have 3 possible choices for 0. We can have f of x equals 0, f of x equals 1, and f of x equals 2. A degree 1 polynomial is of the form c0 plus c1 times x, where c1 is not equal to 0. So we can have f of x equals 0 plus 1x. We can also have 0 plus 2x, 1 plus 1x, 1 plus 2x, 2 plus 1x, and 2 plus 2x. A degree 2 polynomial is of the form c0 plus c1x plus c2 x squared, where c2 is not equal to 0. So we can have f of x equals 0 plus 0x plus x squared, or 0 plus 0x plus 2x squared, 0 plus 1x plus x squared, 0 plus 1x plus 2x squared, 0 plus 2x plus x squared, 0 plus 2x plus 2x squared. And now we list these 6 equations again. It's with 1 instead of 0. So we have 1 plus 0x plus x squared, 1 plus 0x plus 2x squared, 1 plus 1x plus x squared, 1x plus 2x squared, 1 plus 2x plus x squared, 1 plus 2x plus 2x squared. And also 2 plus 0x plus 1x squared, 2 plus 0x plus 2x squared, 2 plus 1x plus x squared, 2 plus 1x plus 2x squared, 2 plus 2x plus x squared, and 2 plus 2x plus 2x squared. So in total, we have 3 degree 1 polynomials, or degree 0 polynomials, sorry. We have 6 degree 1 polynomials, and we have 3 times 6, which is 18 degree 2 polynomials. Here we want to establish a correspondence between the polynomials we listed in parts 2 through 4 with the functions that we listed in part 1. So to do this, we simply evaluate our polynomials at the points 0, 1, and 2. So f of x equals 0 is 0 at all 3 points. Similarly, for f of x equals 1, we have 1s, and f of x equals 2, we have 2s. Now, for f of x equals x, we get 0, 1, 2. For x plus 1, we get 1, 2, 0. And x plus 2, we get 2, 0, 1. For 2x, we get 0, 2, and 2 times 2, which is 4, which is 1, mod 3. 2x plus 1 gives us 1, 0, 2. 2x plus 2 gives us 2, 1, 0. X squared gives us 0, 1, and 1. X squared plus 1 is 1, 2, 2. X squared plus 2 is 2, 0, 0. X squared plus x is 0, 2, and 2 times 2 is 4, plus 2 is 6, which is 0, mod 3. Adding 1 to the previous row, one more time, and etc. What we should find is that each polynomial corresponds to a unique function. So therefore, there is a one-to-one correspondence between polynomials of degree 2 with all possible functions from GF3 to itself. To see if the polynomial x cubed is a new function from GF3 to itself, we must evaluate it at the points 0, 1, and 2. So f of 0 is 0, f of 1 is 1, and f of 2 is 2 cubed, which is congruent to 2 modulo 3. Now looking at these three y values, we should see that they correspond to the polynomial f of x equals x. So therefore this is not a new function. Now in general, we can transform a polynomial of degree greater than or equal to 3 to an equivalent polynomial of degree at most 2. And we can do this using Fermat's little theorem. The statement of the theorem tells us that a to the p is congruent to a modulo p if p is a prime. Now let's say we have a polynomial of degree n, Pn of x. It consists of a term of degree n, so we have Cn times x to the n, plus some polynomial of degree at most n plus n minus 1. Now let's look at the term x to the n. We can write x to the n is equal to x cubed times x to the n minus 3. Now applying Fermat's little theorem to x cubed, we have this equals x times x to the n minus 3, which is x to the n minus 2. So therefore, we have reduced the polynomial of degree n to a polynomial of degree at most n minus 1. Now we keep applying this process to the highest order term until we arrive at a polynomial of degree at most 2. Let's see if it's possible to multiply two non-zero polynomials, call them p1 of x and p2 of x, to get a third polynomial, p1 of x times p2 of x, that is 0. So we evaluate these three polynomials at x equals 0, x equals 1, and x equals 2. So if the product of p1 and p2 is identically 0, then that means p1 or p2 has to be 0 at each of these x values. So let's just arbitrarily fill in some of these blanks. So let p1 of 0 be 0, p2 of 1 be 0, and let's just have p2 of 2 be 0. Now, p2 of 0 must be non-zero, otherwise it would be the 0 polynomial. So let's fill in 2 here, and let's just fill in 1 and 2 for p1. So now we have that p1 times p2 is identically 0. p1 turns out to be the polynomial x, and p2 happens to be the quadratic x squared plus 2. So now we have found two polynomials whose product is the 0 polynomial.